In this video, we are going to discuss about the hack CPU implementation. First of all, let me show you the code for the hack CPU. This is what a code for the hack CPU chips look like. In this video, we are going to discuss in detail about how every instruction of this CPU chip is executed. So let us talk about the input and the output of the CPU chip. This CPU chip has three inputs: a 16-bit IM, which is from the data memory, a 16-bit instruction, which will perform the execution, which is the instruction that is to be performed during the whole program, which is stored in the instruction memory, and we have a reset, which will decide whether to restart the program or not. And this reset, if suppose the reset value is 1, then the program is to be restarted. And if the current program that is being executed and the value of the reset during that time is 0, then the current program will be continued to be executed. Then we have four output for this chip: outem, which is a 16-bit output, that is the value of the data memory. Then we have a 1-bit writem, which allows us to write in the data memory. Then we have a 15-bit address, which is the address where the outem is to be stored. And then we have a PC, which is a 15-bit output, which gives the address of the next instruction. So let us understand the code line by line. First of all, we have to note it, which is to decide whether the instruction is an A instruction or a C instruction. And that is done by using the most significant bit, that is the 15th bit. And suppose the 15th bit is 1, then it is a C instruction. And C instruction can be further divided into three parts, or you can say four: opcode, computation, destination, and jump. And A instruction can be divided into two parts: opcode and the instruction. And this to not yet is used to determine the whether the instruction is an instruction or a C instruction. So the first not yet takes the 15th most bit, that is the most significant bit, and negate it to find out whether it is an instruction or not. And suppose whatever the output from the first not yet will be the input from the for the next not yet, and it will be performed and will be checked whether it is a C instruction or not. Suppose the output is not an instruction, so the not gate will show is 0 in the output, and after being negated in the next not gate, we get to know that it is an C instruction. So that how this two code line works. Then we have an AND gate, which is to determine whether the output is to be stored in the A register or not. And we know that the AND gate only gives the output when both of its condition of the input is to be satisfied. And for that to be satisfied, we need the instruction to be a C instruction. And the fifth mode bit in the instruction, that is the D1 bit of the destination code. And just let I will show you what I meant by D1. So the destination bit, that suppose here we are given this 16-bit binary code, and this red part, as you can see here, is the destination bit code, which determine where the values to be stored in the destination. And according to the destination bit column table, we know that if the value of the D1 bit is 1, so the value is to be stored in the A register. And hence, with the value, if both the instruction, that is the instruction is the instruction which is one of the input, and the fifth most bit in the instruction, and the fifth most bit of the instruction, that is the D1 bit, if its value is 1, then the output is to be stored in the A register. Then we have a mux 16 bit to perform the selection, which is to decide whether the value that is to be stored in the A register will be the instruction or the output from the ALU chip. And similarly, the selection is done by the selection bit, from that is the output of the NAND gate. And in the next instruction, we have an OR gate, which is to output the lower bit for the A register. And we know that the OR inputs the value true only if one of its input is true. That's suppose then we can say that whether even if one of its condition of the input is satisfied, then we will get the load bit chip for the A register. In the next instruction, we have an inbuilt chip of the A register, which has the input A region, and load is load A, which are the outputs from the MUX 16-bit chip that we have discussed above, and from the OR gate that we have discussed just before this particular instruction. The output that will be executed that we will get by the A register is the A out. Then in the next instruction we have a MUX 16-bit chip which will perform the selection just to decide what memory register is to be fed into the ALU. From the diagram, we all know from this particular diagram, we all know that the input to the ALU is the D register and A/M register. And whether the A register is going to or whether the M register is going to be the input for the ALU, and that is decided by this particular MUX 16-bit. So this MUX 16-bit chip will decide whether the input for the ALU will be D register or the M register. Next, we have an AND gate, which is to determine the load bit for the D register. Now, D register is used to store the value of the ALU output. And we know that the AND gate performs the true output the true only both of its instruction is true, and hence we need to have the instruction as the instruction and the fourth most bit of the instruction to be true, and the fourth most bit of the instruction data is the D2 bit. And the table that I've shown you before, in this table the D2 bit, if it is one, then the value is to be stored in the D register. So the mux chip will decide whether the load bit for the D register is to be enabled or not. So we know the mux chip, the AND gate. Then we have a D register, which has the input A register, that is the AL out, and the load, we have the load B. This load bit will decide whether the ALU output will be stored in the D register or not. In the next instruction, we have an ALU chip, built-in chip, which will perform the necessary functions that every ALU chip performs. So this is input that has been given in this ALU will be performing the computation according to their needs and will be giving us an output ALU of. The ZR and NG are the properties which define the output. In the next 3-bit code, which composes of the two OR gates and one AND gate, now this whole 3-bit 3-line code works together to decide whether or not we can write in the data memory. The first OR gate gives us an address M output, which is the address where the output M is to be stored. The next OR gate will give us the value out M, which is to be stored in the address given us by the output address M. Then we have an AND gate, which will gives us the output write M, which is a 1-bit output, which allows us to write in the data memory. In the next two instructions, the next instruction is basically to check the jump condition, which is to be used in the program counter. The next 3-line instruction altogether works to specify the condition that is to be needed to output this JGT3, that is the jump condition. And if the ALU output is will be greater than 0, then the PC will jump to the address specified by the A register, which is done in the above instruction. The next 2-line instruction in which we have used an 2 OR gate is to just to decide whether the jump will take place or not. As we know, the OR will output a true value if any one of its function is true, and hence, even if any one of the following condition of the input is true, then the jump condition will also be satisfied, and the PC will jump to the specified address. In the next 3-line code, we have an AND gate, one NOT gate, and a PC chip. The AND gate is to determine whether the PC is to be loaded or not. Even if one of the PC, the AND gate will decide whether the output is to be whether the PC is to be loaded or not. If both of the condition in the AND gate is satisfied, then the lower bit for the PC is enabled. Then we have a NOT gate, which is to fulfill a case. Suppose we don't need any jump. Suppose the instruction that is given to us, there is no need for any jump. So in that case, the PC will just be incremented by the value 1 and will perform the next instruction that is stored in its instruction memory. Then we have a PC inbuilt which will perform the necessary computation according to the input that it is receiving, along with the load bit, PC load, and a reset button reset, which will output a 14-bit address where the jump has to be taken place. So that is all in this. So that is how the hex CPU bit is implemented. Thank you.